evening, everyone, to the fifth lecture or fifth presentation in our seminar series for Inquisitive Minds. My name is Mike Milgram. I'm one half of the committee of two that's organized this. As I look around the audience here, I see that about half the people have been to the previous talks, and they know what I'm going to say, and they're wondering how I'm going to say it differently. And so I'm not going to say it in the same way as I did before. The idea being that we have a town full of interesting people doing interesting things, and the purpose of this talk of this series is to give them a platform. And the reason I'm not going to give you the ground rules is because we have had such a reasonable turnout that I've managed to find at least 6 people now who are prepared to give presentations next year, so I don't have to strong-arm anyone. If you see me walking down the street, you don't have to go to the other side of the road. I'm not going to try and twist your arm. I still have, as I said, I have 6 people who are willing to give talks next year, and I have a few maybes. So if you have an overwhelming desire to talk within the next year, to give a presentation within the next year, please see me or Naomi quickly, or as soon as possible. Just to give you a bit of background, our first talk last September was Steve Dion, who talked about forest fires, followed by Charles Packer, who gave a lecture on the 7th century poem Beowulf. Bill Diamond talked about how to make medical isotopes from accelerators, and Dave Winfield talked about the history of the slowpoke reactor. Tonight, Alistair Miller is going to tell us about hydrogen. Next month, we are going to learn about the mathematics of backgammon. And I have to say, I actually went on the internet and learned the rules. So anybody who's planning on attending that talk, I recommend you do the same thing. The final talk will be given by Ruben Marini on how to build a battery backup for your house. And for anybody who looks ahead and has marked their calendar, please make a note. We had a scheduling conflict, and Ruben's talk is now put forward by 1 week. It will be on May the 3rd. So if you've marked your calendar, please correct it. I have a CV here for, oh yes, I'm sorry. I've encouraged Elizabeth to encourage you all to have coffee at the beginning, and I want to make this as informal as possible. We're trying an experiment here. We do not have an entrance fee, we have an exit fee. And hopefully you will make your opinion of the speaker's presentation known as you leave. There's a jar as you leave. So far we've collected $400 and some odd for the food bank, and tonight's collection will go to the food bank. So, I've known Alistair for quite a while, since I came here anyway, and we were fighting for computer time on the old CDC 6600. Alistair received his Bachelor of Science in Applied Chemistry from the University of Glasgow, Scotland, a PhD in Chemical Engineering from the University of London, Imperial College. He's a Fellow of the Chemical Institute of Canada and the former President of the Canadian Society for Chemical Engineering. For anybody who's wondering about the relevance of hydrogen and chemical engineering to Atomic Energy of Canada, I want to cast your minds back to the 1970s and 1980s when AECL was going to sell hundreds of reactors, and they needed heavy water to make them run. And there was a whole series of crises during that period. Basically, how could they AECL produce heavy water, which of course is an isotope of hydrogen. So that is the connection. He is today an emeritus for the Atomic Energy of Canada, retired in 2005 with a 40-year employment career. His main interests now are designing and modeling processes for heavy water production and promoting appropriate rules for hydrogen as a non-greenhouse gas fuel for transportation. He is a consultant for Hydrail, the hydrogen fuel cell power for trains on suburban rail networks around Toronto, for Metrolinx, and he has extensive collaboration with AECL CNI and provides consultation to the IAEA on heavy water topics. He was a technical authority for AECL's $20 million industrial prototype with Air Liquide for heavy water production based on heavy water processes, and he was the chemical engineering branch manager at AECL from 1982 to 2002. So I think he knows a little bit about hydrogen. In fact, I couldn't think of anyone better to give us a talk on the subject. Alistair says he will take questions at the end unless you have an overriding desire to get an immediate answer for something that is that needs clarification. So, Alistair?
Well, thank you, Mike. I'm reminded about another talk that I gave many, many years ago in the old auditorium at the plant, and it was to a relatively young audience, and I wanted to demonstrate what hydrogen was like and how safe it actually was. And so I got a beautiful copper cylinder with a cap to it, and I filled it up with hydrogen in building 250, for those of you who know the plant, and then had a bit of an argument with security to get it through the gatehouse out. But however, I won the argument, and I then was able to demonstrate to people how harmless hydrogen was by opening the top of this and putting a flame into it, and it went pop just the way you expect it to do. It's not nearly as dangerous as you might think. But anyway, I remember that as being an interesting experience. I haven't got any hydrogen to actually demonstrate it with you this evening. That would be a little bit more difficult. So, hydrogen. The colours, the roles, and the issues. This is an outline of what I'm going to be talking about. Why we're interested in hydrogen in the first place, the greenhouse gas crisis. I'm going to spend a little bit of time on that because it really is, I think, something that I can't really talk about too much. Then I'm going to talk about how we produce hydrogen and how we should use it and where we should use it. And at the very end, a little coda, twists on the story. Can we drill for the stuff? And what happens if it leaks? Okay, so to start off with greenhouse gases and global warming. I put that in red, the problem facing our planet. No argument in my mind at all about that. Is by far the biggest problem we have. Hydrogen, I think, is a necessary but partial solution. It complements electric batteries. Nuclear energy, again, the experts are pretty much unanimous on this, that unless we have nuclear energy, the whole process is fated to fail. Not the only source of energy, but as I'll explain later on, hydrogen makes it relatively easy to complement nuclear with variable wind and solar. For the benefit of those of you who have forgotten the chemistry that you had in high school, some of the cast: hydrogen H2, water H2O, CO2, carbon dioxide, CH4, methane, basically natural gas, nitrous oxide, the most nitrogen-rich of the nitrogen oxides, ammonia, you'll see where it comes in later on, and then one that you're perhaps not quite so familiar with, the hydroxyl radical. And the ones that I've starred are greenhouse gases. I'll talk a little bit more about how greenhouse gases work in a moment, but I've double-starred water because many people don't appreciate that the greenhouse gas, which has far the biggest impact, is water vapor. Temperature of this planet is about 15 Celsius on average. If it wasn't for water vapor, it would be about minus 18. Water vapor provides us with a greenhouse blanket. And the others, carbon dioxide, methane, nitrous oxide, and a few other minor characters, in fact amplify the effect of water vapor as a greenhouse gas because they heat the atmosphere, and it holds more water vapor and amplifies the effect of water vapor in terms of its greenhouse gas effect. About half of the effect of global warming comes, in fact, indirectly through water vapor that is added as a result of the others. Hydroxyl radical is important. The hydroxyl radical sort of lives for about a second. It's continuously formed in the atmosphere by absorption of ionizing radiation, and it is the main remover of methane from the atmosphere. Reaction that takes the methane out in about a 12-year half-life. And I put in this other arrow as well, because this is a point that we'll come back to later on, but it's important to appreciate that hydrogen can also compete for the services of the hydroxyl radical. And so there is a concern that by possibly adding hydrogen to the atmosphere, there's a little bit of hydrogen in the atmosphere anyway, but by adding extra, if we were to leak it while we produce it, we'd be competing with the methane for the more or less finite supply of hydroxyl radicals. So we have to be careful how we actually handle the hydrogen and not leak it excessively. It's a secondary consideration. It's not a big issue, but still, that's why the hydroxyl radical is important and hydrogen leakage is important. Reminder of the background of these bad actors, the main bad actors in terms of greenhouse gases. The one that's over there is carbon dioxide, and you can see how it climbs monotonously. It started off naturally about 280 parts per million. When I was born, it was about 300 parts per million, and you can see it's now over 420. It's an enormous increase. Fortunately, from our point of view, the effect is not linear, it's more of a logarithmic effect, but nonetheless, this is serious in terms of the driver, the main driver of greenhouse gases. Over here, oh, I'm sorry. Behave. There we are. I've got to poke the right bit. We have methane, and you can see that it was increasing quite steadily. It seemed to level off for reasons that aren't understood in the period around the noughties, but it's been taking off again since then, and so it's a considerable concern because it's a very powerful greenhouse gas, although it doesn't last nearly as long as carbon dioxide. Carbon dioxide persists in the atmosphere for in excess of 100 years. Methane, 12 years. Makes it complicated in terms of defining just how much of an effect these different gases have. But the short answer to this is that from the point of view of the near term, methane is important. It sort of fades away afterwards, but we should be paying extra attention to methane, to natural gas leakage, because it's a big actor early on, even as it fades away later. And then we've got nitrous oxide down there, also climbing steadily. And just to clarify what's actually happening in the atmosphere, because the explanations that you normally hear tend to be confusing. And I try and make it clear in as simple a form as I can of what's really going on. If we look here at the incoming sun radiation, unless the planet were to be perpetually getting warmer and warmer, that 240 watts per meter squared has to get out again. And it gets out, comes in as relatively short wavelengths that are not particularly absorbed in the atmosphere, they're a little bit scattered by clouds. It goes out again as infrared radiation. So those two, that one in, that one out, have to balance. There's a little bit of pickup of heat in the oceans, but we can forget about that for a moment. Okay, it comes in quite straightforwardly, and then it tries to get out. And by adding greenhouse gases, some of it gets absorbed on the way. Now, it's not absorbed and lost, it's absorbed and re-radiated in all directions. Some of it still goes up, but some goes back down again and warms the surface. And so to achieve the balance between the 240 coming in and the 240 going out, which we have to have, the surface has to get warmer. And that, the surface of the troposphere, the lowest part of the atmosphere, that's greenhouse warming. And that's how it works. And this is the choice that's facing humanity. These are from the Intergovernmental Panel on Climate Change. We can have the one on the left, which is the 1.5 Celsius increase that you hear about all the time. And these are for the end of this century, the last couple of decades. We can have that one if we really behave ourselves and curtail the emission of greenhouse gases, or if we just carry on as usual and we axe the tax and all the other silly things that politicians tend to say, then we get that. Now, that's about 1.5 average warming. But you'll see if you look at it closely that the warming is actually about double over land as it is over the oceans. The oceans are 70% of the planet's surface. So land can warm up quite a bit without moving the average very much. And you also see that at the high Arctic latitudes, there is further enhanced warming. So about ×2 over land, about ×4 over the high Arctic. Antarctica, relatively protected in this scenario because it's got a great ice cap that goes very high. But if we carry on as we're carrying on at the moment, then you have this situation. And you can see now extreme rise in temperature in this part of the world in excess of 4 degrees. And if you thought that this winter was mild, you haven't seen anything yet. So that's the problem. If you want to see it in a graphical form, on averages, we can either have the orange ones, that's the carrying on with totally bad behavior. And I should say that we are showing some signs of improving our behavior. It's nowhere near enough, but we are beginning to level off the emissions of CO2 and methane and all the others. But it's not enough just to level off. We have to get right back down and curtail something in excess of 80% of what we're emitting if we're going to level things off and produce this situation. That's the best situation that the ICPP has envisaged. Now, there's another one. You will sometimes hear about the ideas of reducing the incoming solar radiation by putting aerosols in the troposphere or even putting reflectors into space, which would balance a little bit the incoming radiation. Wouldn't have an awful lot, because we know what happens when you have an eruption of major volcanic activity. Tends to cool things off for a couple of years. It does nothing, however, to this other problem, the ocean acidification problem. Add CO2 to the atmosphere, it's in equilibrium with the oceans. About 30% of the CO2 that we emit actually ends up dissolved in the oceans. Nice, you might say, in that it's helping us to buffer our bad behavior, but unfortunately, from the point of view of the organisms that are in the ocean, it's very bad news. It's only so far about 0.1 of a pH, but it's a logarithmic scale. And in fact, it is, as I say, more or less proportional to the concentration in the atmosphere. So we've added about 50% extra CO2. And from the point of view of creatures in the ocean that depend on carbonate shells, things are beginning to dissolve. The foraminifera, the tiny zooplankton animals that have carbonate shells, and they capture CO2 in a way that's actually very useful to us, because when they die, their carbonate shells sink to the bottom of the ocean and take the CO2 out. They're having problems. Great range of them. They're not all in desperate trouble so far, but it's a worry. And we're making things already a little bit more acidic, but look where we are going. Not just 0.1, but we've got another 0.3 or so to go, and that would be absolutely catastrophic. Those foraminifera I don't know what the past participle of that, they're at the absolute, the bottom of the ocean food chain. And if they go, then fish will be seriously disrupted as well. There'll be secondary effects, coral reefs will go, and not just to mention, the photosynthesis, which produces about 30% of the planet's oxygen, will suffer in the process as well, because the phytoplankton will also suffer. Okay, so we have to get off this kind of behavior. So how do we do it? You've heard, and this is the subject of the talk in a glib sort of way, about these various kinds of hydrogen. Green, pink, grey, blue, turquoise, and white. Grey, the bad one, and has variations, brown and black, but they're all much the same sort of way. The way we make hydrogen at the moment is predominantly by steam methane reforming, or slight variations on it. And we start with natural gas, we add steam to that, we produce 4 hydrogens for every molecule of methane, and we produce a molecule of CO2. And if that was all that we were doing, and it is what we're doing just now, producing hydrogen, it would be worse than just burning the methane itself. That's a steam methane reformer in the picture at the bottom. Blue hydrogen, same scheme, but now the idea is that the CO2 is separated and sent into permanent underground storage, where, if you're lucky and everything's working really well, in about 100 years it will react chemically with silicate rock and will form carbonate rock. That's a process, incidentally, that happens naturally anyway on the surface at a relatively low level. CO2 interacts with silicate rocks on the surface, produces carbonate rock, the rock is weathered, the CO2 is captured, far too slow to be really useful, but it does happen. But CO2's underground behavior is quite uncertain, and it can be unsatisfactory. We'll talk a little bit in a few moments about the Sleipner situation in Norway. But anyway, this is an example of carbon capture and storage applied to production of hydrogen by steam methane reforming. Carrying on with this blue hydrogen, as they describe it, we do have some experience. In southern Saskatchewan, a place called Weyburn, they've actually been sequestering CO2, sort of, for more than 20 years now. They inject the CO2, which is actually coming from the Dakotas, into, in this case, an oil formation, and they're using it to enhance the production of oil, and about half of the CO2 comes back up again. So it's not really a terribly good demonstration. It does work, and it does produce oil, and it seems to be worth doing, but it's less than satisfactory as a demonstration of permanent sequestration of CO2 geologically. The idea is that we would inject the CO2 into either abandoned oil or gas formations. That would be good because we know that they're tight. The gas and the oil have been there for a long time. Or a little bit less certainly into deep saline aquifers, where it would be expected to dissolve and ultimately convert. If it works, the cost is estimated to be in that sort of 60 to 100 US dollars a ton, which fits fairly well with the proposed Canadian carbon price at 170 Canadian dollars per ton in 2030, assuming we continue in that direction. But the uncertainty is the security of retention. I said Weyburn, not really terribly convincing. Look at the bottom, however. Oh, sorry. That's roughly what we're emitting. Weyburn itself is 2 megatons a year, CO2 pumped down. One comes back up again, compared to 37,000 megatons per year released globally. And again, in that same context, Alberta is trying to demonstrate that it can produce oil and process oil in a way that is friendly and neutral by collecting CO2 into this 240 kilometre long pipeline, and they aim to sequester about 15 megatons per year of CO2. Drop in the bucket, but well, it's an interesting idea. And again, put it into these old oil and gas reservoirs where it will presumably stay, or once you've used those up, into deep saline, hope that it behaves itself there, which is, I mentioned already, Sleipner, this natural gas field off the Norwegian coast. And it's been running for some time. The deal was that the gas itself is somewhat contaminated with carbon dioxide. So they have to separate the CO2 before they send it ashore. And the deal was that they would inject the separated CO2 into a cat geological layer underneath. And it worked very well for about 16 years. But now we're finding CO2 is finding its way into the gas wells. And so it's not quite as good as they had hoped it would be. So there are problems with sequestering CO2. It's not impossible, but it's certainly not easy. Which brings me to the next color, turquoise hydrogen. I believe, in fact, it probably was my coining this particular description of it. As best I can make out, I was the first person to call it that. Anyway, the idea is that instead of converting CH4 with steam to hydrogen and carbon dioxide, you just heat it up. Most molecules, if you heat them up enough, will actually dissociate. And methane actually is one of the easier ones to dissociate. So heat it up to about 800 degrees, and you will produce hydrogen and carbon. And the carbon is in the form of graphite. It's solid, easy to separate from the hydrogen that you've produced. It's amazingly stable, and so you can, if we go on to the next one, you can find various industrial uses for it, but once you've run out of industrial uses, you can just throw it around. And it will persist unchanged for hundreds of years, and we know about that because the native people in the Amazon had a slash and burn type of existence going back hundreds of years, and the carbon that they left behind is still there, just the way it was when they actually deposited it. So it is a solution that works. The downside to it, however, is that you only get about a little over half as much hydrogen. However, it's something that perhaps will appeal to the natural gas people. It is a way that you can continue to use natural gas without the collateral effect. And it works particularly well in North America because we have an imbalance. We've had it for ages and ages between the energy cost of natural gas and the cost of oil. If you compared them just on the energy that's available, a barrel of oil ought to translate into about 6 gigajoules of natural gas. 1 to 6. But the current factor is actually 1 to 50. So natural gas is remarkably cheap. And even if you end up throwing away half the hydrogen by using the turquoise approach, then it's still quite competitive, and compared to, say, burning diesel in a heavy-duty truck, you'd be ahead. So this one's attracting a lot of attention, and they're looking at all sorts of different ways that this might be done. You can do it catalytically, you always have to have heat, or you can do it with pyrolysis, injecting relatively high energy as plasma. Okay, the big actor in all of this, however, is green hydrogen, where you make it by water electrolysis. The snag here is that it's very energy intensive, taking about 4 or 5 times as much energy as the turquoise hydrogen. So, to make it work, you have to utilize electricity that has little or negative value. Good news, we've got some of that. We'll come on to that in a moment. The stored energy can then power mobile applications. You need a power source, obviously, and as I've said earlier on, more or less everyone's agreed that you have to have nuclear for that. But one of the studies that we did back about 25 years ago showed that you could integrate the variables, wind and solar, with the nuclear in substantial quantities, using hydrogen as a sort of flywheel to take advantage of the variability of the wind and solar and the base of the nuclear to balance off an oscillating demand for electricity. And I'll show you that in a moment. If, and this is where pink comes in, if the electricity comes from nuclear, then the anti-nuke types have described it as pink, therefore they don't like it quite as much. But anyway, pink hydrogen is just green hydrogen with nuclear as the source of the electricity. Electrolyzers, Canada is big in this. The main types use liquid water, and the top one, this one, is aiming for relatively large scale and low cost, because if you're going to take advantage of electricity that is low cost, you're going to have to accept intermittency, and having a low capital cost goes well with that. It uses slightly more electricity. It's just passing an electric current through a potassium hydroxide solution, sort of thing that you probably do in high school chemistry as a demonstration of how you can dissociate a compound. That has a considerable attraction to me personally, because it could well be the basis for quite extensive production of hydrogen in Canada, particularly in the Maritimes, and for shipping hydrogen in a way that I'll describe a little bit later to Europe, particularly to Germany. And if that were done on a gigawatt scale, then one could produce heavy water on the side in a particularly attractive process. So I like this particular approach. Somewhat more sophisticated, you can use what is effectively the reverse of a fuel cell. We'll talk about those later on. Much more compact, much more expensive, uses a proton conducting membrane, slightly less electricity. Another Canadian company, Hydrogen Optimized, is Canadian, so is Next Hydrogen. We have a long tradition of producing hydrogen in interesting ways. The Americans try hard though. They're really keen on high temperature steam electrolysis. And again, it's a little bit like a fuel cell, but it's running backwards. And in this particular case, we'll talk about fuel cells later, don't worry about it too much just now. But in this particular case, they're using a membrane that conducts oxygen. And the idea is that steam goes in here, and the oxygen can go through the membrane there, but the electrons can't. And so hydrogen comes out on this side, the electron has to match up on the other side here to these oxygen ions that are going through there to produce the oxygen that's going to be emitted, and you get a current. In the fuel cell, it's going one way. In the electrolysis, it's going the other way. In this case, you're applying current to actually drive the oxygen through and produce the hydrogen. Okay, I said that the variability of wind and solar had to be accommodated. A lot of people, everyone understands that the wind doesn't always blow and that the sun doesn't always shine. But it's not quite so well known that the total amount of energy on average that is available from wind in particular, which is the orange bars here, is far more available in the winter months than it is in the summer. And by one of those unfortunate coincidences, the demand for electricity in Ontario actually peaks in the summer nowadays for air conditioning, and it's likely to get worse. So there's a very serious mismatch here, and that leads us on to the need for, in fact, the increasing quantity of wind power in particular in the Ontario grid system. The yellow line is the average amount of, the total amount of wind that's actually installed, and this is what it's doing to the frequency with which the electricity is actually of negative value, and we're actually paying the Americans to take it away. So there is an opportunity here to turn that excess electricity into hydrogen. And we did a study of the potential for using hydrogen to fuel the suburban trains around Toronto for Metrolinx. I'll show you a slide in a moment of that. But the electricity was going to be produced, as the bars show, the time of day in hour long, and you can see that almost all of the hydrogen was being produced in the small hours through the night, when the price was extremely low. I essentially said that already. You need a power source that's always available, but you can certainly incorporate some of the variable stuff, as this study, which I mentioned already, back around year 2000, we looked at accommodating 20% of wind as it actually was being recorded in Ontario with nuclear. And we demonstrated that you could go from all of the electricity to all of it in hydrogen with an average value of the orange line at the top. Well, and it worked rather nicely. So it's not a question of just plain nuclear or just plain wind and solar, but you can actually combine the two, and it works out from an economic point of view, at least with the numbers that we use there. Very briefly, there are some exotic ways of making hydrogen as well by splitting water. This is the sulfur iodine cycle. I'm not going to go into the details. You can talk to me later if you want to know what they are. It's a process that has been extensively researched in East Asia, South Korea, China, and Japan, and it involves iodine. And if you've ever had to deal with iodine in the lab, you know that it's badly behaved stuff. And that's a real problem, because you have to cycle it round and round and round, and it misbehaves horribly. Nearer to home, Chalk River spent quite a lot of time working on the copper chloride cycle, where, unlike the sulfur iodine cycle, which is based purely on heat, this one actually uses some electricity as well. One of the steps requires about 0.7 volts there, rather than the usual 1.8 to 2 volts of straight electrolysis. And it cycles between various copper chloride species, copper oxychloride as well, and it does work, but the economics don't look brilliantly promising. But anyway, people try. By and large, I think we're stuck back with plain water electrolysis. So what shall we do with it after we've electrolyzed our water, we've produced the hydrogen? I'm emphasizing that the future is not hydrogen in its own. The future is a judicious balance between electric and hydrogen produced from that electricity. Battery-powered electric vehicles, many of you have one way or another already experienced this with your cars, if they're hybrids or even pure electric. For cars, this is the right way to go. In any sort of light-duty vehicle, it's perfectly feasible to put enough battery power in that you can go fair old distance, quite sufficient, and the faster charging that's available now. The only downside to this is that it remains far heavier than hydrogen if you were doing it that way, but you can live with that on a light vehicle. Perhaps a bigger issue, this lithium supply worries people somewhat. Is there enough lithium out there to really solidly convert the light-duty vehicles entirely to battery electric? But there are other possibilities. That may not be an overwhelming objection. You can use sodium, and there's certainly lots of that around. But batteries can't go everywhere. So there are heavy-duty applications. Trains, heavy-duty trucks, ships, ultimately planes, and perhaps seasonal storage of electricity. I like this because if you look at the bottom, you will see that it's dated in 1999, and there was a conference organised, a relatively short time frame in Ottawa at the time, and Chalk River was asked to provide a paper, and so I did this study at the time in a very simplistic, high-level sort of way as to where one would deploy hydrogen to get off carbon-based fuels. And I ranked them by these various factors on a ratio, on a scale of 1 to 5, 1 being bad, 5 being good, and summed up the totals down here that said that trains were the best place. I didn't, oddly enough, put buses on, but anyway, trains had its consequences, because that then led to the Americans picking up this idea, and so in a sort of way, Hydrail was born for hydrogen fuel cell powered trains. Well, talk again about fuel cells in a short time. Canadian technology again. This is light rail in Germany, the so-called, what's its name? It escapes me. But anyway, it's powered by hydrogenic fuel cells, can operate all day, 1,000-kilometre range, running on hydrogen with fuel cells. It's been in service in Lower Saxony since 2018, and actually they ran one of those in eastern Quebec this last summer. Canadian again. It's still based in Mississauga as Hydrogenics, although it's now owned by Cummins Diesel. Yeah, there's the name, the Cordia Lint. Cordia Lint Island. Okay, what is important to remember in terms of using hydrogen as fuel? Well, it's the lightest element, as you all know, with molecular weight of 2, and it has an enormous energy content on a weight basis. It's 3 times as much as you get from gasoline or kerosene, or natural gas for that matter. But it's bulky, and so you have to be concerned about how you actually store it. And you can see the numbers there. Even if you compress it to 700 atmospheres, which is more or less the standard technique, either 350 or 700 atmospheres, you're still a long way less dense than you are with gasoline in terms of energy content. You can liquefy hydrogen, but it takes about an extra 1/3 of energy to go there, and for most purposes I don't think it's the right approach, with probably the exception of aircraft. It burns with a colourless flame, which is a little bit different from what you're used to, so it's a little bit dangerous that way. If you actually see it burning, you don't see it, other than just a little bit of heat disturbance in the air. It's easily ignited, we know that, wide flammability range, but it's not actually nearly as explosive as perhaps people think. For example, the famous example of the Hindenburg wasn't actually a hydrogen explosion. It was a deflagration that was initiated, people believe, in the actual skin of the airship. That was what caught fire, not the hydrogen in the first place. It's quite hard to make it explode. Unfortunately, though, it's terrestrially almost always in that combined form, mostly water, but also as methane or oil. So you have to treat it as an energy vector. It's not a primary source. And because of that, there are substantial losses in the pathways to energy via hydrogen. In some ways, though, it's good. The actual weight compared to batteries, hydrogen has a 100-fold advantage, which obviously is tremendously useful if you're trying to use it to fuel planes. It can be stored in underground caverns, just like natural gas is stored on a seasonal basis. And with almost a century of experience with doing that, it works really well. Most of the natural gas is stored in salt domes. You pump in water and you hollow out a cavern, pump the water out with the salt with it, and you're left with a more or less impervious container that just sits down there in the ground, and you put natural gas in when you are producing it in the summer when you're not using very much, and take it out for the winter heating period. And as I say, there's almost a century of experience in storing hydrogen that way in a place in the east of England. But in red, the conversion is relatively inefficient. So again, we come back to this need to have low-cost electricity going in if you want to produce hydrogen at an affordable price. But fortunately, that's not too difficult to do. As I said already, best stored, these relatively high-pressure gases, the technology for that is well established. Extra energy if you want to go to liquid, but then this interesting one at the bottom, liquid ammonia. And this is increasingly seen as a way to ship it intercontinentally. The Germans, as I mentioned earlier on, really keen to have hydrogen from Canada, and it would almost certainly be shipped as ammonia. Easy to convert hydrogen into ammonia, it's a standard approach, and then you can crack the ammonia at the other end quite easily, or you can even use it as fertilizer in the first place, at least small quantities. But You have to be careful if you're going to use it in an internal combustion engine that you don't end up emitting nitrous oxide, which of course is a nasty greenhouse gas. Okay, I did promise to say something about fuel cells, because fuel cells are the obvious way to utilize hydrogen. And you put hydrogen in on one side, and you have, in this case, a membrane that is unlike the one that you saw earlier on, where oxygen can permeate through. This one is a membrane where hydrogen can permeate through, but oxygen can't, and electrons, more importantly, can't. So the hydrogen goes through the membrane to the side on the right, and the electrons find their way around on the outside in an electric circuit, and that's where you get your electricity out of this. And again, we can be proud of this in a Canadian perspective, because the leading technology for fuel cell development resides in Canada, particularly in Ballard, but Hydrogenics, again, the people who provided the fuel cells for the Island train, have gone through what painstaking, I'm not putting it there for no light reason. It has been a tremendously detailed, protracted process stretched over decades to deal with all of the issues: conversion efficiency, lifetime certainly, capital costs definitely, and most difficult of all from the Canadian point of view, low temperature operation. And Ballard in particular have really come out on top of that. And so the technology, in the case of Hydrogenics for the Island trains, but extensively in buses in China, it's the Ballard technology, and there are thousands of hydrogen-fueled buses operating with Ballard fuel cells. You can use hydrogen as a fuel in a diesel engine fairly easily, but the power plant now is the original size, and the energy conversion is somewhat inferior, and it also is liable to produce NOx, including N2O. So I've got, I think, three slides that show details from Ballard, proudly displaying their technology. That's out of date now. It's well over 1,500 now in operation, buses, trucks and trains. Really important thing about this is that they are tiny compared to an internal combustion engine. When we did a study for the Metrolinx people around Toronto for their trains, we found that by taking out the diesel engine from the locomotives, we could put in a fuel cell, and all the remaining space was quite sufficient to store the hydrogen that was needed, even though hydrogen is relatively hard to compress down. So the small size of the fuel cells is important. Lowering the cost, durability, small footprint, and then the ability to freeze start from -25°C at an amazing accomplishment. Remember, you're producing water in this process, and you're -25. So I think that's particularly impressive. And in this case, it's an updated slide, over 3,000 fuel cell buses and trucks. Just a few of the examples running around in various places in the world: Japan, South Korea, London. And this is the Metrolinx study that I mentioned. The concept that Metrolinx has of enhanced high-frequency service radiating around Union Station, and they accepted that the alternative to electrification using conventional overhead wires could indeed work with fuel cells. Unfortunately, because it was different, they came to the conclusion at the end that they'd rather go with the overhead catenaries, despite the fact that overhead catenaries have a notorious reputation for costing far, far more than they're supposed to. And the first ice storm that you have, the first train that runs there, the catenaries all come down, and it's a sort of sad bit of interruption to service and costs of fixing. Worse than that, peak demand is at just the point at which peak demand for electricity is elsewhere. And one of the beauties, as you saw in that slide earlier on, for making the hydrogen is you collect the energy in the small hours of the morning, and you then use the hydrogen when you need it. And you're not burdening the system with an extra demand of electricity as you would do if you were running the catenaries. Quite a lot of electricity needed, but in this case we're using the surplus electricity. Well, rather a shame that, for the moment at least, this was a study that they said, yes, it could do it, but we don't want to do it because we'd like to do it the conventional way. A bit further off in the future, hydrogen, as I said, is light, very light. And so here are some conceptual plane designs. Airbus concept in the top left, it's a turbofan, that one. Turboprop down in the bottom, and that rather futuristic blended wing one to provide extra space for storage of the hydrogen. Does need that extra 1/3 of energy to liquefy it, but it's light. And there's a nice little twist to this story. Way back about 1990, Lockheed did a study of what you could do with the cold that was emitted, produced when you were actually vaporizing the liquid hydrogen. And they put it along the leading edges, and they found that it substantially reduced the drag by about 10%. So there's an extra benefit there. You would have thought perhaps it would have caused icing, but you do this when you're up in the stratosphere, which is very dry, and it's not an issue. A little bit extra. Lighter planes with fuel cells will come sooner, I think, but that perhaps is the future in the second half of this century. Almost at the end, but I would like to emphasize that hydrogen really is a safe fuel. Vast experience with liquid hydrogen with NASA since 1958. It disperses very rapidly if it is released, as it has such a low vapor density. It needs education probably to be applied widely, but it is something that we've handled quite cheerfully at Chalk River for decades, and we've never had any serious incidents. And we're well placed to go the electric to hydrogen route. The orange is low emitting sources, nuclear and hydraulic particularly. The only bad actors are Saskatchewan and Alberta, but both of those, I'm happy to say, are now seriously looking at nuclear. Because we have a big nuclear renaissance appearing. And Ontario, as you know, has just agreed to retube the 4 Pickering B reactors. They're putting 4 300 megawatt electric small modular reactors at Darlington, and they're going to add additional 1,000 megawatt reactors at Bruce. We hope they will be can-dos, but that's not certain at this stage. Even Quebec is considering restarting Gentil 2. And as I said, Saskatchewan, Alberta, New Brunswick, OPG, all collaborating in the development of small SMRs. Partly because OPG at least sees a big export potential for small modular reactors. Poland is apparently particularly interested. And hydrogen features in the output mixes from all of those. Little coda at the end, which I promised you. White hydrogen. Recently, people have been finding that if you drill relatively deep, you can find more or less pure hydrogen down there in the lower strata. It's had been thought that it would be improbable because microbes eat hydrogen. Hydrogen, when it actually gets released to the atmosphere, about 70% of it actually gets eaten by microbes in the soil. Only about 30% is left over to be consumed by the hydroxyl radical. So people thought, yeah, we probably can produce hydrogen, but it won't make it to the surface. And that's probably true, because relatively deep drill holes have found more or less pure hydrogen. And it's presumably because we're having a reaction between iron in the rocks and water that has found its way down there at relatively high temperatures. DOE in the US is backing more research into this. As I said earlier on, we've got to worry a little bit about making the hydrogen behave, but I don't think this is a big issue, because at the very worst, we might end up giving up 10% of the advantage of hydrogen because of competition with methane, more likely 1%. So that's it. I couldn't resist putting up the 2 pictures on the left. These are views, the bottom one of, that actually is Saturn viewed in a sort of pseudo ultraviolet because it's Lyman alpha radiation. But you can see there's lots of hydrogen out there. It's just unfortunate that we can't get our hands on it. And they're in deeper space, very deep space, where the wavelength has been stretched by expansion. More hydrogen, the stuff that's red. So that's it. Questions? Discussion? Yeah. Yes?
What about methanol made from direct carbon capture and hydrogen as a vehicle fuel as opposed to battery electric?
Well, methanol, of course, is bad in that when you consume it, the CO2 gets produced and released.
But it would be a virtuous cycle if it was direct capture.
Yes, but you know, that's the object of the exercise is to minimize CO2. You're right. I mean, it can be done, but I think ammonia is actually a much better vector than methanol.
But you have to keep it at some low temperature.
Slightly lower temperature. It's not a difficult temperature to handle. I mean, ammonia is a widely used substance, both as a fertilizer and in refrigeration. Yeah, compared to liquid hydrogen, it's a breeze. Liquid hydrogen, 20 kelvins, minus 253 Celsius.
You didn't mention storage in a hydride.
Yeah, you can store it as a hydride, but of course it immediately is much heavier. And there is a bit of a problem with storage as hydride in that if you're going to cycle it in and out, then the metal breaks down into a very fine powder. So that, yeah, it's possible, but it's really not one that has shown much in the way of commitment. Storing it as a gas at 350 or 700 bar, relatively straightforward. The tanks are fairly expensive, but they're not unreasonably so. And where you have vehicles that are fueled by hydrogen, it's generally stored as a gas like that. Tom?
Can you quantify the efficiencies going from electrolysis, electricity to hydrogen, and then from hydrogen?
About 35%.
What percent?
Yeah. Yeah. You'll lose
35%?
35. 35. Yeah. Yeah.
So is that going from electricity to hydrogen?
Electricity to hydrogen and back to electricity.
Okay. Then can you break
A
it
full
down?
cycle.
Okay, give it to me the two components. What's the first component? Electrolysis to hydrogen. What is that in component?
Sorry?
Can you give me the whole cycle percentage, 35?
35 is for the complete cycle.
Right.
Electricity, hydrogen, back to electricity.
Okay, so what is the fuel, hydrogen to using a fuel cell? What's the efficiency there?
Hydrogen too? I've got a
Using
bad
hydrogen
cold that
in
is
a
making me
fuel-
difficult
Using
to
hydrogen in a fuel cell, what's the efficiency of the fuel?
It's about 50-50 between the two, so we're losing a third almost in both. Yeah.
A friend of mine hydrogenated his golf cart in his garage as part of a startup. And then the company died when they got a golden contract from Canadian Tire because they could not rent any industrial space the moment that landlords heard the word hydrogen due to the Hindenburg effect. So I'm
Yeah.
wondering what are your thoughts on overcoming that?
The usual education. The Hindenburg is always held up as this horrible example, and the Hindenburg, as I tried to point out, really wasn't a hydrogen event. Yeah, hydrogen burnt. More than half the people on the Hindenburg actually survived. There was no explosion. It was just a bit of a bonfire. Sad and regrettable from the point of view of hydrogen's reputation, but like most fuels, it can burn, and that is an isolated example. A Challenger is another example of hydrogen burning, but again, it wasn't really the hydrogen's fault in the first place. If hydrogen is let loose by something else, then it will burn. But then so will gasoline. And if you had a vehicle that was on fire and you were releasing a fuel as a result of that, you're better off with hydrogen. It disperses very rapidly, whereas gasoline or diesel will just pool and burn.
I guess though, for a practical car, the pressure tank gets up to be about 25,000 PSI, if I'm correct. So if that ruptures, that's bad news.
Well, it doesn't rupture. It's an interesting way of doing it. You have basically a reinforced carbon fiber, and it creaks and groans as the pressure changes. But it's been demonstrated you can fire bullets into it, and the thing, well, it'll leak if the bullet hole's in it, but the thing itself doesn't fail and doesn't ignite or anything like that. Ray?
I saw an interesting picture of a hydrogen flame from a vehicle tank. That flame went straight up. None of this cooling or going down underneath the vehicle and roasting people in the vehicle. The flame goes straight up.
That's just a comment, I think, is it?
Yes.
But then there's the parking garage problem.
Make your level.
I was wondering, in what state is the water leaving the hydrogen fuel cell? Is it as a liquid or as a vapor?
Oh, in the
In the fuel cell.
Let me think about that for a moment. In the fuel cell, you're actually putting vapor in, yes.
So you're producing water vapor out of
Yeah.
the tailpipe.
Yeah.
So why would a hydrogen fuel cell vehicle then be better for the environment, since water vapor is
Oh, I see, yeah.
good greenhouse gas?
Sure, but water vapor is in equilibrium with the temperature of the, and if you add extra water vapor, it just rains out, I suppose. Water vapor is very short-lived presence in the atmosphere, and adding extra water vapor, no, not a problem.
But isn't the infrared absorption profile of water vapor much larger?
It's big, yes, but the amount of water vapor in the atmosphere has got nothing to do, other than the temperature of the atmosphere, with injection of water into the atmosphere. It's in steady balance, and we're talking about a turnover in the order of a few days. So if you add some extra water vapor, I suppose it will snow or rain a little bit more locally, but you're not going to add anything just by putting water vapor there. It's temperature-related presence.
If you raise the temperature of the atmosphere, you're just going to cause more evaporation from lakes and rivers and oceans and anything.
Oh, yeah.
So if we don't keep that temperature down, then the water vapor will increase no matter what kind of fuel you use.
Yes, that's basically what's going on. I mean, warmer atmosphere, more water vapor, more greenhouse gas effect from that, but it's got nothing to do with how much water vapor you might actually blow out into the atmosphere. It's strictly temperature controlled.
Well, I'd like to take this opportunity to thank Alistair for this very enlightening talk, and I ask you all to use the traditional